Hello, I'm Mrs. Edwards, and today we're going to go over an application problem of a quadratic equation. Let's go ahead and set up the scenario. We have a basketball player that shoots the ball, and h of t represents the height of the basketball, and t is the time from when it was shot. We're going to go over to something like Desmos.com and make a quick sketch, or grab your graphing calculator and make a quick sketch of this scenario. Along the x-axis, we'd have time, and on the y-axis, we'd have the height of the ball. Okay, that ball is shot, goes up, comes down, hits the ground. And here again, we just have a quick sketch. As we do go through this problem, we will, by hand, find the y-intercept, the vertex, and the x-intercept, and much more. I think it's a really good idea for you to get a quick sketch of the graph before you start a problem, even if you want exact value answers. It allows you to check to see if the answers you're getting seem reasonable. What does the number 4 represent about the path of the basketball? 0, 4 is our coordinate there. 0 is our time and 4 is our height. So at 0 seconds, the height of the ball is 4 feet. In your own words, you might say something like, the ball leaves the shooter's hand 4 feet above the ground. Maybe this is a youth basketball game. Next, we want to answer what time is shot A at its maximum height and what is the maximum height of the ball. In other words, we need the vertex. I'm going to show you two different ways to find the vertex. The first way is a review of what we did in the last lesson, completing the square. To complete the square, the first thing we need to do is verify that that leading coefficient is positive 1. It is not positive 1, it is negative 16. So we're going to take this number over here and we're going to slide it to the side, and we're going to factor out negative 16 out of both of those first two terms. You might be thinking, how can I factor out negative 16 from 23? But remember, when you factor a number out, what you are really doing is just dividing the term by what you are taking out. So negative 16 divided by negative 16 is going to be 1. And 23 divided by negative 16 is negative 23 over 16. Now that we have factored out negative 16 from the front two terms, we're ready to fill in this space to complete the square. To complete the square, we want to take negative 23 over 16 divided by 2 and square it. So let's do a little scratch work over here off to the side. Negative 23 over 16 divided by 2 is the same thing as multiplying by a half. When you multiply by a half, you get negative 23 over 32. When you square that fraction, we get 529 over 1,024. This is the number that completes the square. But we have to keep this balanced, and I can't do what I do to one side to do to the other. So to keep every single line equivalent, I have to turn around and subtract the same value. However, I do not want negative 529 over 1,024 in here, because only these three terms create the perfect square. So I've got to take this and get it out of here. To move it to the outside, I have to remember that the effect of placing it there, it's getting multiplied by negative 16. So if I take it out from inside parentheses and move it over here, I'm going to have to multiply it by negative 16. So I'm moving it over and multiplying it by negative 16 to keep this equivalent. Just simplified there a little bit. 529 over, negative 529 over 1,024 multiplied by negative 16 is 529 over 64. This first part is a perfect square. Simplifying, 4 plus 529 over 64 is my 785 over 64. And then we are ultimately factoring this, which is pretty challenging if you don't know the pattern. The number that goes here is always half of this one. We did that over here in our scratch work. What was the number before I squared it? Negative 23 over 32. It is not a coincidence. That's the number that goes there. You could verify the work. You could multiply t minus 23 over 32 times t minus 23 over 32. Foil it together and you would be right back there. Now that we have this in vertex form, we can of course pick out the vertex. So our vertex here is the opposite of this number, so 23 over 32, comma, and then 785 over 64. Now that we have the vertex, we can answer these two questions. At what time is the shot at its maximum height? Well, the time is going to be 23 over 32 seconds. What is the maximum height of the ball? That's the y-coordinate there, 786 over 64. You could find the decimal equivalent if you would like, but I'm going for exact value answers. In this particular example, I think there's a much easier way than completing the square to find the vertex. If we start with the a t squared plus bt plus c form here, and we want to find when the ball reaches the maximum height. The formula negative b over 2a gives us the x-coordinate of the vertex. Okay, so here we have that, and I'm just going to substitute. My a is negative 16, my b is 23, and my c is 4. Make those substitutions. Simplify. And notice we have the same answer. Oh, I think that is much faster. It just depends if it says complete the square to find the vertex, to practice completing the square. Now that we have the time when the ball reaches the maximum height, we could substitute the time into the function to find the height that it is at that time. I'm going to substitute 23 over 32 into this equation, and then we're going to simplify, and we find out that h of 23 over 32 is 785 over 64, and notice we have the same answer. So this is just another technique of finding the vertex if you're starting with that ax squared plus bx plus c form. How long is the ball going to be in the air? Let's take a look at the graph to estimate what our answer is going to be. So the ball leaves the player's hand at 4 feet, and then it goes up and it comes down and it hits the ground right here, and the time is a little bit after 1.5. So the ball is going to be in the air a little more than 1.5 seconds. If we want to find the exact value here, what do we need to do to use this equation? Well, when does the ball hit the ground? Well, how high? The only variables we have in this equation is the time, which is what we're trying to figure out, and our only other input is the height. So if we want to know the time when it hits the ground, what's the height of the ball when it hits the ground? Yes, 0. So since the height of the ball when it hits the ground is 0, this question, how long is it in the air, is the same thing as saying, what's the time when the height is 0? So we're going to replace the y-coordinate, the h of t there, with 0. Now we have an equation to solve that will lead to how long the ball is in the air. To solve this equation, let's use the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, let's substitute those values. Simplify. And then 785, we would want to double check if we could simplify the square root of 785. So for example, I divided that by 5 and I get 157. And 157, we're not going to be able to break this down and get a pair of factors to take one out. So that's as far as we can go. The question is, if we want the exact value, what's our final answer going to be? So I'm going to go ahead and just estimate really quick. I took the square root of 785 and got the 28.01785145. And then I break that into two separate problems. I'm going to take negative 23 plus 28, etc. there, and I get the positive 5. And then if I do negative 23 minus 28 something there, I get this negative 50. Then I go ahead and divide, and I get these two numbers. All right, we got two answers to the quadratic. Let's think about what that means. Which one seems reasonable? We already decided that the ball was going to hit the ground a little after 1.5 seconds. So clearly this is the one that is our answer. But why did we get another one? Okay, if we follow that parabola and we keep on going, it's going to cross the x-axis at negative 0.157. That is not in the domain of this story problem because this equation only represents the flight of the ball from when it leaves the player's hand until it hits the ground. After that, this equation does not indicate the location of the ball. So this one right there, we're throwing out. And if I want the exact value answer rather than the 1.593, this is our time. I think it looks kind of crazy with all these negatives. It is the correct answer. But if I multiplied the numerator and denominator by -1, I might write this answer instead. If we were settling for an estimate, that would be about 1.593 seconds. When is the shot 7 feet off the ground? Again, let's look at our graph just to estimate our answers. Here's a horizontal line at 7, and right about there, that is, here the ball is 4 feet, it's climbing, it's at 7 feet, and so on, back down to 7 feet, and then it hits the ground. So notice from our picture, we can tell that we're going to have two answers. Let's say the question was, when is the shot 2 feet off the ground? Well, if it was only 2 feet off the ground, 2 feet on this side, that is lower than when it left the player's hand. So if it was 2 feet, we would only have a single answer. That's why making a sketch is handy, just so we know ahead of time what our answer should approximately be. Let's go ahead and actually estimate those. What are the times that go with a height of 7? That looks to me like around 0.15 and 1.25. That's just a rough estimate. Here's the equation we're going to use to find the exact value. So we want the time when the height was 7. We're going to replace h of t with 7 and solve. To solve a quadratic, you always want to move everything to one side equal to 0. So I'm going to subtract 7 from both sides. This new equation, negative 16t squared plus 23t minus 3, does not represent the path of the ball anymore. We are just solving an equation that's going to give us the times when the ball was 7 feet. To solve, we're going to use the quadratic formula again. Let's pop those numbers in there. Simplify. These are the final answers. Notice one more time right here, we have two different times where the ball is 7 feet off the ground. So those are our exact times. You might even at that point say, well, again, I don't like that there's so many negatives. So if you multiply the numerator and denominator by a -1, this would become positive 23. The plus or minus multiplied by a negative would still plus or minus. So we'd have positive 23 plus or minus the square root of 337 all over positive 32. If I was checking with the back of the book, I call him Bob. If you were checking with Bob, Bob would probably have 23 plus or minus the square root of 337 over 32. Let's go ahead though and just find the estimate to make sure that these two numbers seem reasonable. I go ahead and find what is the square root of 337, and I get that 18.357, etc. And then I break that into two separate problems. Negative 23 plus 18 point something there is this negative 4.6. Negative 23 minus 18 point something is this negative 41. I go ahead and do the division, and I get these values. That looks pretty reasonable. We originally estimated that the ball was 7 feet off the ground at about 0.15 feet and about 1.25 feet. So we do know these estimates are great. So if you were looking for an estimate rather than an exact value, that's what we'd have. Last question, about how many seconds after the shot reached its maximum height until it hit the ground? Well, there is the time it reached its maximum height. I'm just going with an estimate here, the time that it hit the ground. So the amount of time that went by from when it was at the maximum until it hit the ground is going to be the difference between those x coordinates. So I subtracted those, and it was about 0.9 seconds.